Chapter 5 Atmospheric Structure and Radiation Transfer. Section 5.1 Evolution of the Earth's Atmosphere. The Earth's atmosphere has gone through three major stages. In the early part of Earth's history, we get what's known as the early atmosphere. This atmosphere occurred from 4.4 to 4 billion years ago and was mainly a response to the cooling of the Earth and the degassing of rocks as they cooled. The early atmosphere was mainly composed of water vapor, carbon dioxide, carbon monoxide, ammonia, nitrogen, methane, and sulfur in two gas forms, SO2 and S2. The secondary atmosphere developed about 4 billion years ago and lasted for about 1.5 billion years. The secondary atmosphere was mainly composed of water vapor, carbon dioxide, nitrogen as the main gases. Now, this atmosphere, the constituents are very similar to the current atmosphere, except for one gas is missing, oxygen. With the advent of life, oxygen started entering into the atmosphere and started building up. So the last stage of atmospheric development is called the living atmosphere. It starts about 5.5 billion years ago and lasts till today. In order of importance, the main gases in this living atmosphere were nitrogen in the form of N2, oxygen in the form of O2, argon, and carbon dioxide. The concentration of oxygen in the atmosphere became fixed at about 20% by about 40 million years ago. Section 5.2 Composition of the Atmosphere. So what I'll be describing here is the composition of the current atmosphere, and I'll go into greater depth about what gases are found in the atmosphere. And keep in mind that the atmosphere is a mixture of gases. In the lower atmosphere, all of these gases are mixed together. They're not separated. The table that will appear in the next slide will show the 11 most common gases in the lower atmosphere by volume in terms of percentage. So the most common gas is nitrogen in the form of N2. 78.08% of the atmosphere is this gas. The next most popular gas is oxygen, O2, at about 21%. Water varies in the atmosphere anywhere from 0 to 4%, and it's mainly a function of temperature. So we're talking about water vapor. The fourth most common gas is argon at about 0.93%. The next important gas is carbon dioxide at 0.039, then neon at 0.0018%, helium at 0.0005%, methane at 0.0014%, hydrogen at 0.0005%, nitrous oxide at 0.00003%, and the last gas on our list is ozone at 0.00004%. Now the gases that have the red star in front of their name, we can call these variable gases. Their concentration either changes in the short term, like water vapor, or it is changed over the last few hundred years because of human activities. The gases that have changed because of human activities include carbon dioxide, methane, nitrous oxide, and ozone. So in this slide we see a pie chart. It's useful because it kind of gives us a good fast visual picture of the how much of these main gases, nitrogen and oxygen and argon, make up relative to the other gases. So approximately 99 6% of the atmosphere is nitrogen, and oxygen, and argon, and all of the other gases in our table, which included about 8 gases, only make up 0.04%. Let's now look at some of the main gases and talk about some of their interesting characteristics as they relate to us and other living organisms. So as I mentioned, nitrogen and oxygen are the main components of the atmosphere by volume. Together, these two gases make up about 99% of the dry atmosphere, so if we leave water vapor out. Both of these gases are very important to life. Nitrogen is the main nutrient that is taken up by the roots of plant organisms to feed them. Nitrogen is a limiting nutrient. It controls growth. Nitrogen is removed from the atmosphere by biomass burning, and it's also removed by bacterial action. It is deposited to the Earth's surface by specialized nitrogen-fixing bacteria, some of which form symbiotic relationships with plant roots, like legumes, and by way of lightning. So lightning produces this solid forms of nitrogen that fall out with rainwater. So as I said, nitrogen moves from the surface of the Earth, from the biosphere to the atmosphere by two methods, biomass combustion and denitrification. And denitrification is caused by bacteria in moist environments break down solid forms of nitrogen to get energy, releasing nitrogen gas into the atmosphere. Oxygen, which we know makes up almost 21% of the atmosphere, is exchanged between the atmosphere and life by two processes, photosynthesis and respiration. Photosynthesis produces oxygen when plants take in carbon dioxide and water plus sunlight and release oxygen into the atmosphere, and at the same time produce the basic building block, organic building block of life, the glucose molecule. So photosynthesis we know only takes place in plants. All forms of life respire, or all major forms of life respire, and respiration is a process that occurs in mitochondria, where organic molecules are broken down to release energy, and this requires oxygen. So organisms, when they respire, they have to take in oxygen to perform this chemical reaction in the mitochondria. As I said, a water vapor is variable, both spatially and temporally, and you've probably noticed that. Some days it feels very humid out, other days it feels dry. So water vapor moves about the atmosphere with air masses. It also varies considerably with the temperature of the atmosphere. Higher temperature locations usually have a lot more water vapor contained in their air, while colder locations have very little water vapor locked up in the atmosphere. So we find the highest concentrations of water vapor are near the equator, over the oceans, and in tropical rainforests. In cold polar areas and in the subtropical continental deserts, the volume of water vapor can approach 0%. Now back to our table. The fifth most abundant gas on this table is carbon dioxide. So I'm jumping a few gases here. Argon isn't really important for life, but carbon dioxide is. Carbon dioxide is required by plants in order to do photosynthesis, and of course they also require water and radiant energy from the sun, and they produce glucose and oxygen as a byproduct. The volume of carbon dioxide has increased by over 40% in the last 300 years. The main things that are causing this gas to increase in the atmosphere are human activities, the burning of fossil fuels, and our modification of the biosphere by replacing natural vegetation that contains a lot more biomass with smaller biomass cropping systems. So as we know, carbon dioxide is exchanged between the atmosphere with life via photosynthesis and respiration. The following graph shows the change in the concentration of carbon dioxide going back just before 1750. The blue dots represent measurements taken from simple station ice core, and then the red dots are from a recording station that was set up in 1958 on Mauna Loa. So we can see that the increase in carbon dioxide was gentle at first, and then after about 1950 it started increasing exponentially. And the current value of carbon dioxide in the atmosphere is somewhere around 415 parts per million. So it's still increasing. And because we need fossil fuels in our society today for energy generation, it's going to continue to increase probably for many decades until we move towards more renewable energy sources. Carbon dioxide is a very strong greenhouse gas. It's also been increasing because of human activities, and it's increased since 1700 by more than 150%. Human sources of human activities that release methane include rice cultivation, domestic grazing animals are keeping of them, an increase in the number of termites, which is associated with deforestation, landfills, coal mining, and the extraction of oil and gas from beneath the surface of the earth. So here we see the trend in methane from about 1000 AD to 2015. Once again, we can see that starting in about 1800, the trend in the increase changes drastically and becomes much more exponential in nature. There was a short blip around just before the year 2000, lasting for about a decade, where methane kind of stalled in its increase, and it's believed that this is related to the breakdown of the Soviet Union and them basically generating less methane from mining activities and coal extraction, oil extraction, and so on. Nitrous oxide is another greenhouse gas. Its concentration has been increasing at a rate of about 0.2 to 0.3% per year, so not necessarily exponential. Sources include, and these are human sources, land use conversion, our combustion of fossil fuels, biomass burning, and soil fertilization. The process of creating urea, an artificial nitrogen-based fertilizer, produces a lot of nitrous oxide that seeps into the atmosphere. So here is a graph showing the trend or change in nitrous oxide from 1978 to the year 2015. Another gas that we've modified, and it's a greenhouse gas, is ozone. Now we got to be careful here because ozone is a little bit more complex in terms of where it's found. There are natural concentrations in the lower stratosphere, and then there's artificial concentrations that exist around urban areas. And the majority of the ozone that's in the atmosphere is in the stratosphere, about 97%. And this ozone has been, since the 1970s, has been decreasing, especially over Antarctica and to a lesser degree over the Arctic, because of a chemical that we produced artificially called chlorofluorocarbons. And these chlorofluorocarbons reacted in the atmosphere and temporarily removed ozone from the air. This problem is healing. We now have a ban on the production of chlorofluorocarbons. We'll look at this problem in greater depth in Chapter 10. Ozone is also highly concentrated at the Earth's surface in and around cities. And it can either be produced by industrial processes, electrical motors, or is a byproduct of photochemical smog, which is related to the burning of oil at the Earth's surface in cars. And anyways, this ozone is building up in these urban areas, and it's toxic. It's toxic to organisms. It affects their respiratory system. The final thing I want to talk about is not the gases in the atmosphere, but the fact that the atmosphere also contains liquid and solid particles. Many of these particles are the result of human activities. For example, agriculture, or driving vehicles, or the burning of fossil fuels, or the burning of vegetation. We call these particles, liquid and solid particles, aerosols. Now, not all aerosols are the result of human activities. There are some aerosols that are produced naturally. For example, dust coming from desert areas, or pollen is another natural aerosol that enters into the atmosphere. The following slide shows aerosols from North Africa, from desert regions, blowing over the Mediterranean Sea into Italy, Greece, and Turkey, and they're moving with an air mass.